everybody, and welcome back. Today we're going to continue our exploration of matrices and introduce a new concept known as the inverse of a matrix. So we say that A with a -1 up top, which is what we're going to use to denote the inverse of a matrix, is called the inverse of some other matrix A if the product of that inverse matrix times the original matrix is equal to the identity matrix, and the original matrix and the inverse of that matrix is also equal to the identity as well. In some circumstances, for example, if the matrix A is not a square matrix, only one of these is going to hold. In that case, we call it a left or right inverse of that matrix A. But if we're going to mandate that A is a square matrix, then both of these should be holding true, and we will call that matrix A inverse matrix of the original matrix A. So let's just mandate those things up front, and we'll talk about the non-square inverses a little bit later. So let us assume A is a n by n square matrix, and let us consider the associated matrix equation AX is equal to B. So we're going to discuss how inverses of matrices play a part with solutions of systems. So as we already know, if the determinant of that coefficient matrix A is not equal to 0, then the solution of this equation, AX is equal to B, exists and is unique, which is a great thing. So is it possible to represent the solution to this equation with respect to this newly defined inverse operator, or inverse function, or inverse matrix, I guess you could say? So if we have the equation AX is equal to B, what I can do is I can multiply A inverse on the left-hand side of both sides of this equation. So we're going to have A inverse times AX is equal to A inverse times B. As we should already know, matrices are associative, so we can rewrite this equation as the following: A inverse times A times X is equal to A inverse times B. And provided that this inverse does exist, we know that the inverse times that matrix A is going to be equal to the identity matrix. So we have the identity matrix is equal to A inverse times B. And we already know what the identity matrix does to a matrix or a vector. It just reproduces that same exact thing. So once we're done, we're going to have that X is going to be equal to A inverse times B, which is the solution to the original matrix system that we had before. So if the determinant of this coefficient matrix A is not equal to 0, that means this inverse matrix A inverse does exist, and we can write the solution of that system in regard to that particular matrix. So that is very, very important. Now, how can we find the inverse of that matrix? So let's actually look closer at this solution process that we've presented here. So we have AX is equal to B, and more importantly, A inverse is independent of B. It actually only depends on A. So if we write this in a slightly different way, we can actually write this as AX is equal to I times B. Here, A is an n by n matrix. I is an n by n identity matrix. X and B are both column vectors with n rows and one column. So what I can do is I can rewrite this in terms of the other form. So this implies, if A inverse does exist, that this is equal to IX is equal to A inverse times B. So if we look at this again in the same exact light, again, I is an identity matrix, A inverse is an n by n matrix as well. And again, we have X here, and we have B here. Notice that the X's and the B's have not changed positions, but A has moved to the right-hand side and became A inverse, and I has moved to the left-hand side. So if we look at this from the Gauss-Jordan elimination perspective, what we did was we started with the augmented matrix A augmented with I, and then we transformed this into I augmented with A inverse, right? And we already know how to turn the left-hand side of a system into the identity matrix. That can be achieved via Gauss-Jordan elimination. Right? So actually we have a way of finding the inverses of matrices. So let's start off with the easy example, and let's start off with a 2x2 matrix and see if we can derive a very shortcut way of finding the inverse of that 2x2 matrix. So the matrix that we're going to be looking for the inverse of first is going to be this nice little 2 by 2 matrix with A, B, C, and D as its entries. So what matrix A inverse do we need to multiply A by, both on the left and on the right, in order to produce the 2 by 2 identity? Now in order for this inverse to exist, we're going to mandate the determinant of that 2 by 2 matrix A, which we already know is going to be equal to little a d minus b times c, is this cannot be equal to 0. So as long as that's not equal to 0, this inverse is going to exist, so let's get started with that. So the first thing that I want to do is present this in augmented form with the 2 by 2 identity. So it's going to be equal to A, B, C, D augmented with 1, 0, 0, and 1. So in order to do Gauss-Jordan elimination on this, our first goal is to eliminate that element C in that bottom corner to turn this into an upper triangular system. So the least common multiple of A and C, generally, as long as they're relatively prime, is going to be the product of A and C. So what I want to do is I'm going to do C times row 1 minus A times row 2, and that's going to produce my new row 2. Let's actually walk through that very abstract calculation here. So what is that going to give us? So C times row 1 minus A times row 2 is going to be equal to 0 because that's actually just the same thing. The second column is going to be equal to C times row 1 minus A times row 2. So that's just going to be equal to CB minus AD. And then 3, that's going to be equal to C times row 1 minus A times row 2, so that's going to just be equal to C. And then the fourth column, that's just going to be equal to C times row 1 minus A times row 2, so that's going to be equal to minus A. So that's going to be the first, or the new second row that we're going to achieve from that. So that's going to give us what? So let's actually write that out. So it's going to give us A, B, 0, and then we're going to have BC minus AD augmented with, so our old first row is going to be 1, 0, and then we're going to have C minus A. Okay, so that's the first element of Gauss-Jordan elimination. Now we're just going to divide by everything by BC minus AD. So once we do that, what are we going to have? So we're going to have AB01 augmented with 1, 0. Then we're going to have C divided by BC minus AD, and minus A divided by BC minus AD. But what I want to do is notice that BC minus AD is the opposite of AD minus BC, which is just the opposite of the determinant of the original matrix. So what I can do is I can rewrite that as A, B, 0, 1, augmented with 1, and then we're going to have negative C all over the determinant of A, and then positive A all over the determinant of A. Let's not forget that little 0 there. Okay, so the next thing that we need to do is eliminate that element B there. So what I can do is I can do row 1 minus B row 2 in order to get our new row 1. All right, so what is that going to give us? So that's going to give us the following. So A minus B times 0, that's just going to be equal to A, and then B minus B times 1, that's just going to give us 0 by design. Now the right-hand side is a little bit exciting. So we're going to have 1 minus the negative C, so it's going to be 1 plus C all over the determinant of A. And then that's going to give us our new row 1. And then 0 minus B times that new quantity at the bottom. That's going to give us our new quantity there. And then that other row is going to remain the same. Okay, so slightly a little complex. So the first thing I want to look at is that entry there. So I'm going to get a common denominator, so I'm going to have determinant of A all over the determinant of A, and then plus C all over the determinant of A. So it's going to be the determinant of A plus C over the determinant of A. So what exactly is that? All right, and actually we are missing one little thing. Where is it? We're missing the B that we multiplied that by. Right? Let's not forget the little b. So once we have that, what are we going to have? So remember, the determinant of A is just going to be equal to AD minus BC, and then we're going to have that BC located there. And notice that these BCs are going to cancel. Okay, so that's pretty nice. So once we have that, what do we have? So A0, 0, 1 augmented with AD over the determinant of A minus AB all over the determinant of A minus C all over the determinant of A, and then A over the determinant of A. And then I'm going to divide everything by A on that first row to get my identity matrix on the left-hand side. And then I'm going to have 1, 0, 0, 1 augmented with, and then I'm going to have D over the determinant of A. And then we're going to have minus B over the determinant of A minus C over the determinant of A, and then A over the determinant of A. Notice that we have a common entry there, so we can factor that out. So that's just going to be 1 over the determinant of A times the matrix D minus B minus C A. And that is the general form for the inverse of our 2 by 2 matrix. So for our 2 by 2 is going to be A, B, C, D. What you do is first find the determinant, divide by it, and switch these two entries and negate the cross diagonal entries, and that is going to give you the determinant of a 2 by 2 matrix, which is actually quite nice. So let's actually look at a numerical example just to see how you would go about that calculation. Let's assume that our matrix A is minus 3, 2, 4, and minus 1. So the determinant of A is going to be equal to A, D, minus B, C. So it's 3 minus 8, which is going to be equal to minus 5. So that means the inverse of this matrix is going to be equal to negative 1/5. So we're going to flip those entries, and then we're going to negate the cross-diagonal entries. Notice that everything is negative, so I can factor out this negative if I want to, just to make it nice. So that means the inverse of this matrix is going to be 1 divided by 5, 2 divided by 5, 4 divided by 5, and 3 divided by 5. And one can show, if that is your original matrix, that A times A inverse and A inverse times A are both going to give you the identity matrix, which is one of the properties that definitely should hold if that truly is the inverse, so you can always check your work on these types of things. Generally speaking, the inverse of a matrix, especially if the number of rows and columns is extremely large, can be very, very tedious to calculate. But there are some matrices that are actually very, very easy to calculate the inverses of. One of those is going to be diagonal matrices. So let's assume D is a diagonal matrix. And again, what do we mean by a diagonal matrix? That means Dij is not equal to 0 for I is equal to j, and Dij is equal to 0 for I not equal to j. All right, so that's the definition of a diagonal matrix. Some people will drop this first requirement and allow zeros to be on the diagonal of that matrix, but as you will see in just a moment, then that diagonal matrix is not invertible, which can sometimes be a bad thing, especially for some later analysis methods. So in particular, let us assume we have the diagonal matrix D, which is equal to D1, D2, down to Dn, and let's assume it has zeros everywhere else inside of this matrix. One can show if you were to multiply this matrix by something in order to get the identity, D1 times something has to be equal to 1, and the only reasonable candidate for that would be its reciprocal, 1 over D1, 1 over D2, all over 1 over Dm. Here you can see why we would want to mandate that the diagonal entries are not 0, because the inverse would be dividing by zeros and hence not existent. So let's actually look at a little numerical example just to illustrate this. Let us assume we have the matrix A, which is equal to the 3 by 3 matrix 1, 4, 0, 0, 0, 3, 0, and 0, 0, minus 2. So if it's not a diagonal matrix, the inverse of this would, of course, be a little bit tedious because you have to use Gauss-Jordan elimination. But using this little principle that we just introduced, the inverse of this matrix is just going to be the reciprocals of the diagonal entries. So it's going to be equal to 4, and then positive 1/3, and then lastly negative 1/2, and then zeros everywhere else. Right, and you can of course justify that by doing A times A inverse and A inverse times A. That's going to give you the identity regardless of which way you do that multiplication. Now let us do an example of a 3 by 3 matrix that isn't diagonal, and moreover it's not upper triangular or lower triangular either. Right, so this of course will be a little bit more tedious in the general case. So our question is, what is the inverse of this 3 by 3 matrix? So the first thing that I want to do is augment this matrix with the identity matrix. So it's going to be equal to 1 minus 1 2, 2 minus 3 3, 1 minus 1 1, augmented with 1 0 0, 0 1 0, and 0 0 1. So Gauss-Jordan elimination, of course, wants us to eliminate the 2 and that 1 in that position. So in order to do that, what operations can you do? So one thing you can do is you can do 2 times row 1 minus row 2, and that's going to give us a new row 2. And then for that, since we have 1 and 1 there, we can just subtract those rows. So row 1 minus row 3, and that's going to give us a new row 3. Once you do that, that's going to give us what? So row 1 is going to remain unchanged. So 1 minus 1, 2, 1, 0, 0. And then we're going to have what? So 0, 1, 1. And don't forget to change the identity side of these things, right? Because we still need to apply that operation to that side. So that's going to give us 2 minus 1, 0. And then on this last row, we're going to have 0, 0, 1, and then 1, 0, minus 1. Now notice in this transformation, we actually have something very nice happen, right? So you should see that we have a 0 in this particular position, right? So therefore we don't need to do like a row 2 versus row 3 kind of manipulation. So we can move on to the upper triangular focus here. In particular, we're going to focus on that 1 and focus on that 2, right? Which is pretty good. So what can we do in order to eliminate that? So notice that we have 1 there and 1 there, so we can just subtract those two directly. So we can do row 2 minus row 3 in order to get a new row 2. And then we have a 2 and a 1 there, and of course the least common multiple would be 2. So we're going to do row 1 minus 2 row 3 in order to generate a new row 1. So row 1 and 2 is going to change. That's going to give us 1 minus 1, 0, 0, 1, 0, and 0, 0, 1, augmented with negative 1, 0, 2, 1, negative 1, 1, and 1, 0, minus 1. There's only one thing left to focus on, and that's going to be that minus 1. So how are we going to do that? Well, we can just add row 2 and row 1 together to eliminate that, which is going to be pretty nice. So let's just write that out just to be formal. So row 1 plus row 2 equals a new row 1. So that's going to generate the identity matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1. And what's on the right should be the inverse of our matrix. So that's going to give us 0, minus 1, 3, 1, minus 1, 1, 1, 0, minus 1. All right, so let's conclude this formally. So if A is equal to the matrix 1, minus 1, 2, 2, minus 3, 3, 1, minus 1, 1, then, via Gauss-Jordan elimination, we have shown that the inverse of this matrix is 0, minus 1, 3, 1, minus 1, 1, 1, 0, minus 1. Sometimes also it's useful, especially if these matrices are really, really large, find the determinant of this original coefficient matrix, because if it's equal to 0, you're going to be wasting your time to find the inverse because it's not going to exist. So if the determinant is equal to 0, don't even bother trying to find the inverse. It's not going to exist. So sometimes that's also often a good starting step for this, just to make sure that you're not wasting your time trying to find something that actually isn't going to appear. The last thing I want to do today is introduce two very important theorems that are often associated to inverses of matrices. The first theorem is going to be the following one. So if A and B are invertible matrices, let's assume that they are invertible square matrices, then the inverse of the product is equal to the backwards product of their inverses. Right? So it's not A inverse times B inverse, it's B inverse times A inverse. If you've taken any abstract algebra courses, this shouldn't come as a shock to you, but if you're not familiar with, matrices, then this might come as a surprise. Keep in mind, AB and BA are not necessarily equal to each other, i.e. Matrices are not necessarily commutative. So if that's the case, then you shouldn't be shocked that AB inverse is not equal to A inverse times B inverse. But if A and B are commutative matrices, then you actually can get this nicer property that AB inverse equals A inverse times B inverse. Right? So let's prove this more general case first. Okay? Proof. So we know that the inverse of the product times the product is going to be equal to the identity. So we're focusing on the product AB here. So we can call it like C. So C inverse times C is going to be equal to the identity, else it wouldn't truly be an identity, would it? So if that is the case, what can we get from this particular identity? So if that is true, we're going to have AB inverse times AB is equal to I. And what I want to do is I want to multiply both sides on the right by B inverse. So we're going to have AB inverse times AB times B inverse is equal to I times B inverse. Now, you may wonder, well, why exactly do I want to do that? You'll see in just a moment. But for first off, notice that we can reassociate these matrices, and B times B inverse is going to be the identity, so that's going to disappear. And B inverse times the identity is just going to be B inverse. So that's going to give us A times B inverse times A is equal to B inverse. Now what I want to do is I want to rearrange this A, and I want to multiply both sides on the right by A inverse. So I'm going to have AB inverse times A inverse is equal to B inverse times A inverse. And now you can sort of see why I wanted to do that in the first place, because that is equal to the identity matrix. And we have that AB inverse is equal to B inverse times A inverse. Right? And that is the result that we sought out to prove, which is actually very nice. For a second theorem, actually, let's take this. So theorem 2. The inverse of the inverse is equal to the original. So to start these off, so we don't accidentally assume what we're trying to prove, so we're actually going to rename that A inverse. We're going to give it a name. Let's call it actually B. Or you can name it whatever you want, as long as it's a friendly name. So we're going to let B be equal to A inverse. Okay, so if B is equal to inverse, what is the inverse of B? What exactly is the inverse of B? So the inverse of B is equal to A. Now, why exactly is that the case? Because B is equal to the inverse of A, that means A is going to be the inverse of B, right? Because if A is the inverse of B, that means A times B is equal to the identity matrix, because keep in mind, B is just a placeholder for A inverse, right? So A times A inverse is equal to I. That means B is the inverse of A. Therefore, we're not really assuming the original theorem here. We're just using the definition of an inverse. So if B is equal to the inverse of A, that means A is also the inverse of B. So if A is the inverse of B, that means B inverse times B is equal to what? Well, if A is the inverse of B, that means B inverse can be represented as A times B. And A times B, since they are inverses, should be equal to the identity matrix, right? So that means, of course, that A is the inverse of B, as we've already stated. So let's actually write that in words. So that means A is equal to the inverse of B. But what exactly is B? Well, B was defined to be equal to A inverse. That means A is equal to the inverse of the matrix, A inverse, which again is what we sought out to prove. Right? So there's some very careful wording and careful logic that you definitely have to be careful of when you're working through that particular proof. But those are two very common proofs that are useful in this particular calculation. So I hope you enjoyed this discussion on inverses of matrices, and I'll see you in the next video. Take care.